afternoon, our interest of today is about physical chemistry, and we are going to look at ionic equilibrium or ionic equilibrium. In these topics of today, we are going to finalize and analyze some of the few concepts that is in our findings of today. My name is Mr. Opio Kenneth, and at the same time a teacher of Elite High School. I want us to look at this degree of ionization for weak electrolytes and ionization constants for weak electrolytes, in this case weak acids and weak base or weak bases. Then we shall also look at the pH and buffer solutions and salt hydrolysis, acid-base indicators, and then acid-based graphs, and how we can come up with the explanation of the graph. Then we shall conclude with the solubilities of sparing soluble salt. Stay tuned. Can we begin with the degree of ionizations? Degree of ionizations is the maximum potential. The maximum potential, in some books they call it the maximum ionization, the maximum dissociation of weak electrolytes. Weak electrolytes dissociation, that is the degree of ionization, is the maximum potential or maximum ionization of weak electrolytes or dissociations of weak electrolytes. Weak electrolytes. Now, in today's findings, we want to know the meaning of weak electrolytes. Many times we have this question is being asked, but we cannot answer. Weak electrolytes simply means an electrolyte which cannot produce as many protons as possible, or cannot produce as many conductants or conducting ions as possible, and therefore they are restricted by numbers of the conductors, which we are calling the ions. Now, in this case, we are looking at majorly the weak base, weak base or weak bases. Weak bases. We are also looking at weak acid. Weak acid, according to Bronsted and Norris, and the Lewis base and the Lewis acids, we all know what a weak acid is. A weak acid substance which releases very few conductants or ions in solutions, and likewise produces very few hydrogen ions in solution. Now, today we are interested in the degree of ionization. As a matter of fact, we'll say the definition is maximum potential of weak electrolytes to produce constituent ions or constituent ions. Take a look. So we have an example of equation that we are yet to look at. For example, here we will come up with, for example, an acid of this kind, and it is appears because for weak electrolytes there must be a high affinity or maximum dilution. That means it should be at a zero concentration, so that there is room for dissociation. So here, since it is a weak electrolyte, we shall use arrows to indicate dissociation of weak electrolytes. And here we shall come up with a proton, and as well as we shall come up with another connector, which is the base. Now here we need to know the initial number of moles, because we are interested in determining the degree of ionization. Now, the initial number of moles, we need to know it by virtue of what we are given. We know 1 mole of weak electrolyte produces constituent ions under maximum dilution. Now here we are going to say 1 mole. Here remaining 1 mole. But initially there was no units or number of moles because these are products of dissociation or ionization. Now we are saying, what about the ionization moles? What about the ionization moles? What about the ionization moles? What do we say about that? Ionization moles would be 1 minus degree of ionization. And here we don't know, but already we can determine it by knowing the number of degree of ionization of this constituent ion produced after their ionization. Then we are also going to be subjected to concentration. Concentrations of weak electrolytes. And in this case, we are saying concentration is represented by C. And that means we shall say C minus alpha. Alpha represents degree of ionization. Alpha represents degree of ionization. Now here we shall say C alpha, and here we shall also say C alpha. Now, in this finding, we are going to use the law of mass action. Law of mass action, so that we can come up with a formula. Law of mass action allows us to use the word equilibrium. Equilibrium. So here we shall call it equilibrium constant. Equilibrium constant. And for this case, we are now branding it as Ka because we are dealing with ionic. Okay? Now here, the Ka is going to give us the concentration of the constituent ion. Concentration. We use a bracket. In this case, we shall say the concentration of hydrogen ions, aqueous, times the concentration of this base, aqueous. And being that there is no connection with that, but we need to indicate it now, that's text, so that they can clearly understood. Dividing it by the concentration of the original solution or original electrolyte. In this case, we have the acid that dissociated to give us that. Now here we can substitute with what we have finally come up with. In this finding, we shall say Ka is equals to the concentrations of hydrogen ions times concentrations of the base all over the concentrations minus or into 1 minus alpha or minus degree of dissociation. Now because there is a common figure here, we can take away this so that we remain with the C into alpha square over 1 minus alpha. This becomes our second final decision making. Now, assumption that we need to take into consideration here is we need to take up an assumption. So we have assumption made. We have assumption made. What assumption do we make here? Since this dissociation is taking place at a maximum concentration of 0 dilution or 0 concentration, that means the concentration of the ions are dynamically equal to the concentration of the reactants. Now here we shall say 1 minus alpha is almost approximately the same as 1. 1 minus alpha is approximately equals to 1, or is as small as 1. That means 1 minus alpha is the same as 1 in this case. Now, what do we take from here? This is assumption that the concentration or the number of moles from here, when we take away the alpha, is almost the same as 1. And that's why we shall have this one equals to this. Therefore, we shall come up with the Ka equals to C alpha square over 1, because we have equated it to be to 1. And therefore, Ka is going to be C alpha square, which is now our finding. But remember, we are interested in alpha. How do we make it as a subject? Therefore, we shall say alpha square is equal to Ka over C. And since we are interested in this, we are going to make this into the square root as well as Ka over C. So that we have alpha equals to the square root of Ka over C. And this becomes our calculation point. This becomes our calculation point, where alpha is the same as degree of ionization. Degree of ionization for weak electrolytes. For weak electrolyte. Then we have Ka is the acid ionization constant. Ionization constant. And then C is equal to the concentrations. Concentrations of weak acid. Thank you so much for attending to this program, and I'm assuring you from here we can now proceed with the calculation. And that is our next subtopic. Bye-bye.